Hi, welcome. So a couple announcements. Friday, there's not going to be an exam. It will be next Monday instead. So the exam will also be in the Ingman lab, which is upstairs. If any of you want to stay after class, I'm happy to walk people up there to see where it is if you need to. So do make sure that you're ready for that. If you would like to bring your own computer and work on your own computer, we might be shy a couple workstations just because of the whole number that is in here. So if you feel comfortable and want to bring that, just let me know as you come into the room on that date. It will be open notes, open book. Topics will be kind of what we've already discussed. Any questions about that upcoming exam and the change in date? Okay. Another announcement, no quiz this week, so this will be an exception because we have the exam on Monday instead. So use Friday, I would suggest use that time to go through the Unit 1 practice problems to prepare for the exam instead. Use that as your self-assessment. Are you understanding the material and can complete that at 100%?
If
Yes.
we have our notes on like our iPad, do we need to print them on a piece of paper to have?
No, you can use your iPad, so it's open calculators, open iPad, especially if you submit your work through your iPad. Yes, so bring your iPads, bring your tablets, bring your own computer if you want. If you want to prepare any material beforehand just to have that ready, feel free to prepare all that material. If you use anything pre-prepared, say you've programmed to have the resistances, you put them in parallel and that form is already there in something. Just make sure you capture it because sometimes I'll get people that make errors in that pre-programmed information. So do make sure you capture that and submit that with your work that you do submit for the exam. Does that make sense? Okay. All right. Any other questions about exam? No quiz this Friday. Okay, so there will be a homework. It is posted and available now. So do make sure that you work on that for Thursday's submission along with the discussion assignment that will be due by Thursday. So those are open now. All right, quick review as far as every element has a voltage and current. What does that mean? So that means for a current source, it has a voltage across it. So make sure to memorize that concept. And whenever you see a current source, you're going to look at that and say, that has a voltage source, or voltage across it, it's unknown, so I have to solve for it. That way, if you take your loop, you're not ignoring that element that has the voltage across it and getting errors based on that. Okay, that's one of the most common errors I see currently at this stage is that people forget that there's a voltage across a current source. So make sure to understand that concept. Understanding extraordinary nodes, ordinary nodes, understanding what a branch is, and that through a branch you have one unique current, but you can have multiple voltages. For parallel branches, you have one voltage across each parallel branch and multiple currents in each branch. So one of the unique currents because there's multiple branches. Does that make sense? So make sure you understand these concepts as they are going to need to be understood to do well on the first exam. Okay. All right, so we are going to today start with equivalent resistances and reviewing those. So go ahead and introduce yourself to your neighbor. If you haven't met your neighbor, go ahead and work with them to determine what this R equivalent is of this first network.
that whole big series, right? Yeah. So this series is parallel. So it would be two. Yeah. So it would be 8 parallel 2 plus. So the one would be separate. So you just add them. So I would redraw this just to make it more clear. So it's going to look like this. And then this simplifies even further after you do that. Parallel. You know, this is becomes 1K plus that parallel.
All right, good job. It looked like everybody was coming to a consensus. One thing I noted, make sure to not forget units. It's very different to have 2.6 versus 2.6K, which would be 2,600 ohms. So those are very different values and you would be marked wrong. So make sure you do put 2.6 kilo ohms on there. But the 2.6 is correct. When you go through this, first I suggest highlighting all of the nodes, then identifying are these extraordinary or ordinary. So this would be an ordinary. What's the green? Extraordinary. And what's the blue? Extraordinary. And then my pathway, I'm actually starting at A. So I'm going to go through this element. Going through an element is a plus, so that's going to be series. When I get to this extraordinary node, that's going to split, which would mean parallel. And then they were going to join at the bottom. So they join into together. And so you can see the extraordinary on the top of green and the extraordinary on the bottom of blue are going to be two parallel branches. So this branch includes these two joined because of the ordinary node by series. And so it would be our equivalent is 1K, which is where I started, 1K, and then again they'll split. So I'm going to have something in parallel with something else, and then you have to determine what are in those branches. So one of them has 8K, and the other branch just has 2K. So then mathematically, 1 over 8K plus 1 over 2K. And this is 1K plus 1.6K to give you 2.6K ohms, or you can write it out as 2,600 ohms. All right, any questions about series parallel configurations? Okay, let's do one more. Again, introduce yourself to your neighbor if you don't know your neighbor, and go ahead and work on these together. Okay, good job. You guys all looked like you got it. Right units also. So going through this, it's a 2, and then it splits. So it's going to be 2 plus whichever of those branches. So my R equivalent from A to B is going to be 2 plus, and I have 2 branches that I know are in parallel. So then you need to determine what are in those branches. So in this one, I just have 2 ohms. Put 2. And in this one, I see that these are separated by ordinary nodes. I forgot to put, these are extraordinary nodes. So I'm going to combine all these into one from the ordinary nodes. So that's going to be 2 plus 2 plus 2 for 6. And then I see that they join again, and then they go through the element of 2 to B. So that's going to be a plus 2. So 2 plus 1 over 2 plus 1 over 6 plus 2 is 2 plus 1.5 plus 2 for 5.5 ohms. All right, any questions about that one? You guys are doing good with the parallel series equivalent resistances. Okay, great. Okay, this one is a little bit different because in the left one, you see that there's not a wire, and then in the second one on the right is a wire. So I kind of wanted to say, like, look at some things that are a little different visually, and then also determine R equivalent for both of those. So we'll call this R equivalent 1, and this R equivalent 2, and go ahead and try and solve for these. There should be 2 ohms. So good job as far as they are both 2 ohms. They're just differently, or they're found differently. So in the first one, you have the left branch is combined by that ordinary node, and the right branch is combined by an ordinary node for 4 ohms and 4 ohms, and then they split right at the beginning. So that's going to be parallel branches. So 4 in parallel with 4, which gives you 2 ohms. In the one on the right, you have an extraordinary node in between them instead. So they split, but the branch is going to be 2 ohms and 2 ohms. So that's going to be your first component, and then they join all it together again, which would then be a plus, and then you're going to join them, or they're going to split again. So it would be plus 2 in parallel with 2. So 1 over 1 over 2 plus 1 over 1 over 2. And each of these is going to be 1, so 1 plus 1 gives you 2 ohms. So they are both 2 ohms, but just found in different configurations. So the first one they're in series, and in the second one they're in parallel, and then added in series. So the equivalents look like this. This one has a resistor, and then this one has, try and draw it the same, let's see. You can draw it either way, but combining these, you have a resistors A to B, and then on this one, when you join them, they look like this. So this is 1 ohm, 1 ohm, and this one has 4 ohms and 4 ohms. So they end up being kind of different circuits. Okay. I wanted to show that just to say visually, be careful about the visual. It can be kind of deceiving, and really make sure you're looking at those node locations and the pathways between them. Okay. All right, any questions? All right. Okay, so now we're going to move to a different one. So determining the current I here. So this is the location of I going in this declared direction. So don't move the direction of the current and find it with that same direction that's labeled. A hint, it's going to be easier to combine things into an equivalent resistance to find this. Sorry. There we go. pathway from A to B, so it comes in, and then it splits, joins again, and then splits again. So this node, you can kind of separate it out, redraw it. Kind of those, and then there's a wire that separates it out.
Oh, I got 25. This. 245 plus 170. Oh. I don't know if it's right just to.
They're joined. They're drawn this way, but they're drawn just, different separate too.
Because like technically all of these are parallel to each other. This would be. It could be like. Could that be written as 60 parallel?
This one, if these two are those two, and then these two be separated out. This one join again. So even though this is all like mirroring each other,
This node splits. This way it wouldn't. Split is still here. So we have I still going into the node. And it's still split.
all of that is
This
the
branch
same
over
location.
here.
So whether it's
30,
drawn like this
this
or if it's drawn like I had it before,
It's still split between the two.
still the same location.
It's the same node. So it's
Interesting. Okay, what is, this one I only had a few responses, so what is, where are you guys getting stuck, I guess, on this? Anybody want to share where it was more difficult to determine how to go from here? Yeah,
I can say the way I did it.
okay.
That's right.
Uh-huh.
So the way that I did it is I found the total resistance around the whole thing, and then
Okay.
I used the Ohm's law with the total resistance and the total voltage. So I would equal V over R. So I got 50 volts over 25 ohms is what I found. So then I got 2 amps of the total current, and then the current has to come out the battery. So I think it's just 2 amps right there.
Correct. So to do that, you needed to find all the equivalent resistances. So this doesn't have an A or B labeled there. So you would want to put your A and B in there and then determine it. So to do the Ohm's law, which is a great way to do that, if you know all the resistances, you know the voltage is set at 50, then it would just be 50 over resistance R. But finding this R equivalent. So to do that, I would say, well, this is my A point, and then I'm going to label the B point and label also a ground. So there would be my B location would be there. So then I would ignore the 50 volts as I'm trying to find this equivalent A to B. And this would be my R equivalent. So to do that, one way is to fully remove it from this circuit and say, what's my pathway from there to there, from A to B? So doing that, then I have, put that ordinary. Highlighting the nodes, and then my pathway starts at A. Oops. And goes through the elements, so that's going to be 5 plus. And then I have a split, so I know these are gonna be in parallel. So I have some branches in parallel. In the first branch, which I go to the left, I notice that these are combined by an ordinary node. So those would be series, so that would be 60. Over here, I'm not quite sure, but I have this. So then I need to take the pathway through those. So going through this, I would be 25 ohms go through it. So this one then is 25 plus something. And then I notice these split, so then that means they're going to be those branches in parallel. And to determine those, I see, well, there's just one element in each, so this is 10 plus 10, or 10 and 10. So now this is 25 plus 1 over 10 plus 1 over 10. This gives me 25 plus 5 for 30. And I can go put that back up into this one. And this gives me 5 plus 1 over 60 plus 1 over 30. What was that again? So that's 5 plus 20 for 25 ohms. So my R equivalent here, this then is 50. So this was 50. And my I goes in this direction, which is plus to minus, which is also going to flow down here, which is the same polarities. So this is also going to be a plus I times R, or plus V over R equivalent for 2 amps. Okay, after I've gone through it now, for those that kind of got stuck, any comments as far as where was the sticking point? Yes.
So I was gonna put you over voltage over REQ, right?
Yep.
And your REQ was 30?
25. So the R equivalent in this branch that was, this is this branch here, whereas 25 plus 10 in parallel with 10, that equivalent was 30. So this equivalent together is 30 ohms,
Oh, I see, okay.
and this is 60 ohms.
Yeah, I missed that last one.
Okay. And then I put that back in the top one, and then that gives me 25 ohms. Okay, questions that people have about this? Seem to be stopping some people. Yes.
I have a question.
Yep.
So is the current negative or positive?
So the current going up is going away from the battery. So when I redrew it, it again is going from that plus to the minus. So the polarities there are the same, because when I draw it down, I can see that the node on the top has the same polarity as the node on the bottom. So because the polarities are the same on the connected nodes, that's going to be plus I times R. Visually, hopefully you can see it when it's drawn in parallel like that. If not, then you would still look at, the polarities are the same here. So my plus and minus was where, I'll take it off, there we go. So the plus is on this plus arrow, and then the negative after it goes through everything is on the opposite side. So because it's starting out with plus, that's another way to determine that it's the same polarity. Does that help?
Yes.
Okay. So yes, it can be a little bit more confusing when you're like, well, I combined everything. Where is my plus and minus on there? So look at the original one and look like where, since it's plus and plus, it's the same.
Okay.
So that would mean a plus polarity. Okay. All right, other questions? Okay. All right, I think this is the completion of that lecture 8 notes. So we're going to move to lecture 9 notes. So let's look at this one. So here you want to find let's find. Let's do I1, I3, and I5. So find I1, I3, and I5. All right, so those were correct answers for those that did get those. Okay, so highlighting nodes. So hopefully you can see, like, yes, they come in, and then the 2 and the 6 on the top are in parallel. And then the 2 on the bottom are in parallel. So noticing that, you know, a current comes in, goes through 2 parallel branches that have only resistors in those branches. So you can use a current divider here. So I1 is going to be 6 is coming in, and then it goes through the 2 ohm, so it's going to be either 1/2 or the opposite branch, and then the summation of both branches. So opposite, and then this is, oops, 1/2, 1/2 plus 1/6. So either of these is going to give you 4.5 amps. So then you notice that it comes together and joins in one wire, and it had 6 amps coming in. That means 6 amps has to go out. So that's why this is 6 amps. So it's going to be the same as coming into those branches. It's got to come out of those branches. Then you notice that the wire splits again. And to find I5, 6 comes in, and then you could do opposite branch over the summation of both branches' resistances, or you can do 1 over 1 over 6, 1 over 2 plus 1 over 6. Either of these, you get 1.5 amp. Another way to look at this is if they split, you already know you have 4.5 going through one and 6 amps total. So the other one has to be 1.5 amps. So either way you look at that, you can solve for those 2 branches. How do you know that it's a plus on each of these for the current? It's the direction of the current that's set, and then you have to look at the direction that the labeling is set. So in this case, as they come in, they're going to be positive if they go down. So all of those are going down, so they're all going to be positive. If one of them was going up in this direction instead, this one would be a negative result. Okay? Questions? Yes.
Is I2 equal to 1.5 as well?
Uh-huh. So this would be 1.5, put it in blue. And this one would be 4.5 amps.
This is a little off the topic, but if you were measuring voltage, would the voltage divide evenly between the parallel circuits?
So how many different voltages are here in the circuit? That's a good question. Three is correct. So I would want to label one of them as ground, but that would be 1 voltage. The voltage here would be a different one, and the voltage here would be a different one. So that would give you 3 different voltages, and the voltage across the 2 ohm on the bottom is going to be which variable? The 2 ohm on the bottom, this one. So what's the voltage across this 2 ohm resistance?
4.5 times 2, so 9.
Okay, which is also going to be V2, right? So the voltage here, and is it plus on the top and minus on the bottom? How do you know?
Direction of current.
Okay, so the direction of current in comparison to 0. So that direction of current goes down, so it's going to be plus on the top. So you would have plus to minus of 4.5 times 2, which equals 9 volts. So V2 is the top node, and if you set that at, you know that's 9 volts, then V2 has got to be 9 volts, which is also the voltage across the 6 ohm. So you could also find that same voltage V2 as I3 times 6. And they're both going to equal 9 volts because they have to both equal the same at the same node.
Yes, that was my question. It divides evenly. They have the same voltage, right?
Across parallel circuits, yes, 1 voltage. So this would be, again, plus on the top and minus. So 6 times 1.5, which is 9 volts. What's the voltage at V1? This is a good exercise to go through. Yes,
Shouldn't it just be 18 because it's the exact same thing?
correct. So you're gonna again have 9 volts across each of these. So V2 is 9 volts from 0, so then V1 is 18 volts. All right, questions on that? That was a good question.
So does that mean if you're doing your ground and going through a parallel circuit, you don't add other side, you just add?
So they're in parallel to each other, so you only add 1.
Okay.
Because both of them have 9 volts across them, but there's different currents going in the different branches. So here you have 9 volts right here, but going through here you have 4.5 amps, and going through here you have 1.5 amps.
So it's resisting it.
So, so they're different resistances. So yes, so you have different resistances, but based on the values of the current and the resistance, they both have the same voltage across them. Does that make more sense visually seeing that?
Yeah, so from going 0 to V2, you don't add full 9s.
Correct. It's just one voltage across both. So 9 volts, and then you have another 9 volts for 18 volts. So once you know current and resistance, they act like a battery. So because they're the same, like, oh, I have two 9 volts here, they're still going to give you just 9 volts across them. Does that make sense? Okay, was there another question? I thought I saw another hand. Okay, we'll continue on with these 9, and then I'll also have another one for 10 posted for Fridays. Is there any requests for particular types of problems? Anybody have requests? Yes.
I think KVL problems would be good.
KVL? Okay.
Just gonna say like KVL voltage loops.
Okay, KVL. I'll definitely have more of those. And there, yeah, I guess if you have any other questions, you can come ask me.